This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the pro version with the unlimited testing center and the free version without the unlimited testing center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it. Hey y'all, what's up? It's the Electrical Code Coach, and I'm super excited to offer this resource to you guys. It's 25 questions with full audio explanations. Before we get started, if you guys could do me a huge personal favor and hit that subscribe button and hit the notification bell button, that way we can spread the word and help more people. With that being said, I want to talk about the best way to use this resource. So each question, I'm going to speak it audibly and it'll list the answers below. But right after I'm done speaking it, go ahead and hit the pause button on the video and try to work through it on your own. And then you can hit the play button and see how I fully explain it and lead to the answer. I am the Electrical Code Coach. And if there's any way that I can help you in life or business, you can just email me at electricalcodecoach@gmail.com. Let's get to it. Let's do one more. How many more, number 10, THWN-2 conductors can you fit inside of a piece of 3/4 inch Schedule 80 PVC if it already contains 3, number 10, THWN-2 conductors inside of it? Remember, we're going to head over to NEC because it's all of the same size and insulation rating. When we get there, we're going to find our type of pipe, and we're going to tee off with the respective page number. Then when we get to that page number, we're going to find our insulation type, our wire size, and our pipe size. Remember, we're doing subtraction here because we need to figure out how many more we can fit. So we're going to find out how many total we can have. Then we're going to subtract that out to find out how many more we can fit. So we take the 7 that the pipe handles. Then we're going to take and minus the 3 that we already have. And that's going to leave us to be allowed to add 4 more to that pipe. And we're going to select A. Great job. All right, this one's a little bit tougher. If you need to slow down, pause the video, and work through, rewind it a few times, that's okay. Just take your time on it. What is the total cubic inch volume you would calculate for a box that contains 8 12-gauge conductors terminating to 2 single-pole switches and 6 14-gauge conductors terminating to 2 single-pole switches in a 4-gang box? All right, so we're just going to take it one step at a time. First thing you do is you figure out your cubic inch volume for each individual conductor. You have the 12 and the 14. 12 is 2.25. And we know that each device yoke counts as 2 of whatever wire is terminating to the device. So in this case, we have 2 devices for 14 gauge and 2 devices for 12 gauge. All right, so we take our 8 base 12 gauge conductors, and we're going to add 4 conductor count to it because each device counts as 2. So that's going to total 12. Then we're going to take 12, multiply it by the individual volume, and that's going to give us 27 total cubic inch count for 12 gauge conductors. Now let's just turn around and do the same thing for the 14. We find out the individual volume. We find out how many device yokes we have. We take our original count, which is 6 14 gauge conductors. We're going to add 4 to that because we have 2 device yokes. That's going to total 10. Then we take 10, multiply it by the individual volume, and that's going to give us 20 total cubic inches for 14. Now we just take and add the 2 together. We take our original 27, add our 20, and that's going to give us 47 cubic inches. And we're going to select D. What is the total demand for 26 ranges with a nameplate rating of 12,000 watts using the standard method? Table 220.55, our range falls in between 8 3/4 and 12, so we're using column C. We slide down on the far left-hand side, head down to 26 ranges. We slide over, and we find out that column C states that we must use 15 kW as our base and then add an additional kW more per range. So we take our 15 kW base. We have 26 ranges, so we add 26. That gives us 41 kW total, and we select B. All right, let's jump into another one. What is the total demand for 9 dryers with a nameplate rating of 4,700 watts each using the standard method? Remember, when we're using the standard method, we'll calculate the dryers at a minimum of 5,000 VAs or the nameplate rating, whichever is greater. In this case, our minimum is 5,000 because our nameplate rating was only 4,700. So we take 9 multiplied by 5,000. That's going to give us 45,000 watts or 45,000 VAs. Then we head to table 220.54 to find out what our demand factor is for 9 dryers. We find out that it's 55%. So we take 45,000, multiply it by 0.55, and that's going to give us 24,750. And we select B. Great job. All right, guys, let's get into the 2020 stuff. And you'll see by the end of the next couple slides that they've really complicated the process for counting this, and they've really gained nothing. So let's go ahead and jump into it. And hopefully by the 2023 code, they will have fixed this. I haven't got any real world feedback of the 2020 testers that they're being tested on this for their exam, but I have to assume that you're going to be, because this is a pretty important part of box fill is, the equipment ground. So let's go ahead and jump into it. What is the total cubic inch volume you would have for a box that contained 7 equipment grounding conductors, all 12 gauge in the 2020? Okay, so for the first equipment grounding conductor all the way up to 4, it's going to count as 1 based off the largest conductor in the box. Then, so for the first 4, it's going to equal 1x, and in this case, the largest conductor is a 12, so it's going to equal 112. Now we have to have a 1/4 inch increase for each conductor past 4. So let's just take it step by step. So the easiest way to do this is to take your total equipment grounding conductors and minus the 4 and see what's left over. In this case, it's going to be 3. So we have to increase 3 by a 1/4 inch each. So we take 3, and I'm going to convert it to decimals so it's easier, and we're going to multiply it by 0.25. Now that's going to give us a 0.75 increase. So it's not even a whole conductor. I'm not understanding, why they did this. So we have a 0.75 increase, not even a whole conductor. Now we have to add that together. We take our original 1 that was counted for the first 4. We add the 0.75. That gives us 1.75 conductors. Now we have to take and bear that math out. Each 12 is rated at 2.25. We take the 1.75, multiply it by 2.25, and that's going to give us 3.9375. The code doesn't address any type of rounding up, so I don't know if we're supposed to round up or what, okay? So we're just going to take that at face value, and we're going to select A. So this is where it gets convoluted. Are we rounding up? What is 0.75 of a conductor? You see what I'm saying? And so if we were in the 2017, we would have counted them all as 1. In the 2020, we've added 0.75 of a conductor. Is that going to be enough to kick us over in box fill? Since it doesn't address rounding up or down, if I have 0.75 over, okay, it really just kind of, just really convolutes things. So let's go ahead. I'm going to show you a little more complex version. And I don't know what they're testing you out in the real world, or if anybody's even caught it, because they might have just, blew through the question, counted all the equipment grounds as 1, and not realized that there's been a change. So let's go ahead and work through one more. What is the smallest device box you could use to fit 4 12-gauge conductors and 3 14-gauge conductors? So the first thing that we're going to do is figure out what is our total cubic inches. So we're going to head to table 314.16b. We're going to find the cubic inch volume for the number 12s and then multiply it by the number that we have. We're going to do the same for the number 14s. Then we're going to take and add those together. Now that is our total cubic inch volume. Now that we have the total, we need to head to our first table that we learned about last week, 314.16a. And this is where the magic happens. Now, anytime you're having one of these questions where you're trying to find the total fill, you can typically use the middle column. Remember I taught you last week called the minimum of volume column. It's the little skinny column right in the middle of that table. Just make sure you're on the right-hand side of that column in the inches cubed and not the centimeters cubed. Now, in order to do this question, we're kind of doing like a reverse lookup question. So what we're going to do is we already have all the information. We just got to find the smallest box. So we need to find the smallest box that will fit it. So the question states what type of box. We're dealing with a device box. So on the left hand, or over in the previous column on the left hand side in the box trade size, we know that we don't need to start looking until we get to where it says device right there. It would be in the fourth column down of the horizontal columns, and it says device, 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 device. So we know it's going to be one of those boxes right there. Now we need to come down into the minimum volume column on the inches cube side, and we're going to get down to where we start to be in the device boxes. Then we just slide down until we find the smallest box that will fit 15 cubic inches. Well, in this case, if you look through all of the device boxes, the only one that will fit 15 cubic inches at all is a 3 by 2 by 3.5 device box, which is going to be allowed to fit 18 total cubic inches. Our question was asking for the smallest box, and in this case, this is the smallest box that can legally fit it. So we're going to select a 3 by 2 by 3.5 device box. Great job. Let's look at it from a different angle. How many number 10 conductors can you fit inside of a 4 11/16 by 1.5 square box? So in this case, it's told us the type of conductor, and it's also told us the box to use. So you're going to start on the left-hand side and find your box first. And when you're doing this, you definitely need to use a sheet of paper or something to come across with so you don't get lost, okay? So first, let's go to the 4 11/16 boxes. It's in the third horizontal column coming down, okay? And we find our box is a 4 11/16 by 1.5. So that's the second box listed there in the 4 11/16 boxes. Now we're going to lay a piece of paper or a ruler or a pencil, something across this as a straight edge so we don't get lost in the sauce. Now we need to come over to number 10 conductors. So we're going to come over and we're going to tee off when we get to the 10 conductor size. And in this case, so we've looked at the table, we're going to find that it will fit 11. You see how we did that? We started on the left-hand side and found our box. Then we came over and we teed off with the size conductor, and we found out that that box will hold 11 10-gauge conductors. Great job. What size overload protection would you select for a 5 horsepower, 208 volt, 3-phase motor terminating to 75 degree C terminals with a nameplate current rating of 16 amps marked with the temperature rise of 35 degrees C? Following the same line of codes, this one is listed with a temperature rise, so we're going to use that respective demand factor. And in this case, it's 125%. So we take our nameplate FLA, we're going to multiply it by 1.25, and that's going to give us 20 amps. Now in this case, they do make a 20 amp breaker or fuse, so we don't have to select the next size down. It happens to fall on the correct size. So we're going to head to 240.6a just to verify. We got a 20 amp fuse or breaker listed there, and we're going to select C. What size short circuit ground fault protection would you select for a 7.5 horsepower, 230 volt AC single phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 37.9 amps using an instantaneous trip breaker? We're going to use our FLC and not the nameplate FLA rating. We're going to head to table 430.248 because it's single phase. We're going to find that we have an FLC of 40 amps. Now we're going to head to table 430.52 and be careful to tee off with our motor. We're going to find out that it's an 800% increase. So we take our 40 multiplied by 8.0. That's going to give us 350 amps. Now we're going to head to table 240.6a and we're going to choose the next size up. And in this case, it falls right on a standard size, which is A. Great job. What size copper conductors would you select for a 10 horsepower, 115 volt, single phase motor that has an FLA nameplate rating of 95 amps terminating to 75 degree C terminals? We're going to go through all of our initial steps. Then when we get here, we're going to change over to table 430.248 because we're dealing with single phase. So when we head there, we do the same process. We find our horsepower, we come over to our voltage, and we're going to find out that this motor has an FLC of 100 amps. Now we have to take that 100 amps and we're going to multiply it by 1.25, and that's going to give us 125. Now we head to our primary ampacity table, and again we're back in the 75 degree C column for copper. We're going to come down until we find a wire that is large enough to handle our 125 amps, and we're going to select D. What is the total general lighting demand after demand factors for a multifamily dwelling unit that has 5 apartments with 1,300 square foot of main living space, a 400 square foot loft bedroom, and a 400 square foot attached garage? Let's go ahead and get our total. We're going to count the 1,300 square foot of main living space. We're going to count the 400 square foot of the loft, and we're going to omit the 400 square foot of the garage. We're going to do that at 3 VAs per square foot. That is our total square foot. Now we multiply that by 3. That's going to give us 5,100. Now we're going to take and add our 2 small appliance and 1 laundry circuit, all calculated at 4,500 VAs total. That's going to give us 5,100 plus 4,500 equals 9,600. That's our total for one apartment. Now we have to multiply that by 5 because we have 5 apartments. That gives us 48,000 VAs. Then we're going to take and apply our demand factors from table 220.42. We take 48,000. We're going to minus 3,000 and set it to the side, and that gives us 45,000 VAs. Now we take that 45,000, we're going to multiply it by 0.35. That's going to give us 15,750. Then we just take and add that back to the 3,000 that we set to the side. That's going to give us a total of 18,750. And we're going to select A. Great job. What is the total HVAC demand you would calculate for a dwelling unit with an AC compressor rated at 22 amps, using a 2.2 blower amp motor, and 5 baseboard heating units rated at 3,500 watts each on a 122/40 volt system using the optional method? So first we're going to calculate the AC. We're going to break that down just like we did in the previous examples, and we are going to calculate the heat. Now we take 5 and multiply that by 3,500. And that's going to give us 17,500. Now we're going to take that and we're going to apply the 40% demand factor. So we take the 17.5 multiplied by 0.40, and that's going to give us 7,000 VAs. Now we're going to select the larger, and we are going to select D. One thing I want to note to you very quickly, and it's kind of a weird catch when you do the 4 or more or the 4 or less. Because if you noticed in the last example, we only had 3 baseboard heaters and the total VAs were 6,825. Well, we added 7,000 more watts by adding 2 more of those units, and it only brought, with the demand factor being allowed to be 40%, it only brought that total demand up 175 VAs. Now that's that little pocket right there in between 3 and 5 heaters, where it doesn't change the demand much because they allow you to do such a larger demand factor. So remember, it was 3 heaters at 3,500 VAs, and it gave us a total of 6,825, and then 5 heaters at 3,500 VAs only gave us a total of 7,000. So that's pretty neat right there in that pocket right there. So let's get to it. What is the total calculated load after demand factors for a dwelling unit that has 1,200 square foot of main living space with the following appliances? A 1,000 watt dishwasher, a 9 kW range, a 5,000 watt dryer, and a gas water heater. So we're going to take and first figure out our square foot VAs. We take 1,200 multiplied by 3, and that's going to give us 3,600. Now we take and add our 4,500 VAs for our 2 small appliance and our 1 laundry circuits. So we're going to take and total those together, and we're going to start a larger math problem over here to the side. Now we take the total of all of our appliances. In this case, they have a gas water heater, so that's not going to be a consideration for us in the load calculation. So we just take the known appliances, we add those out, and that's going to give us 15,000. So we take and add that over to the side. Now we're going to take and total that out. That's going to give us 23,100. Now we're going to do our demand factors. We are going to take 10,000 and set it to the side. So we take our starting total, we minus 10,000, and that's going to give us 13,100. Now we take 13,100, multiply it by the demand factor, which in this case is 0.40, and that's going to give us 5,240 VA in our reduced load. Then we're going to take 10,000, we're going to add back the reduced load, and we are going to get 15,240. And we're going to select A. Great job. What is the total general lighting demand after demand factors for a multifamily dwelling unit that has 10 apartments with 1,700 square foot of main living space and a 400 square foot attached garage? So we're going to count our 1,700 square foot of main living space. We're going to omit the 400 square foot garage. We're going to take and multiply that by 3 VAs per square foot. That's going to equal 5,100 VAs. Now we're going to add our 4,500 VAs for our 2 small appliance and 1 laundry circuit. That's going to give us 5,100 plus 4,500 equals 9,600. Now we're going to take and multiply that by 10 because we have 10 apartments. So we take 9,600 multiplied by 10. That's going to give us 96,000. Now we're going to apply our demand factors from table 220.42. 96,000 minus 3,000, that's going to equal 93,000. Then we take that 93,000, we multiply it by 0.35. That is going to give us 32,550. We're going to take that 3,000 and add it back to our 32,550. That's going to give us a total of 35,550. And we select D. Great job. What is the allowable ampacity of a 2-watt XHHW copper conductor that's installed in an area with an ambient temperature of 68 degrees C? When doing temperature corrections and bundling adjustments, we're going to start in the 90 degrees C column. We find that 2-watt in the 90 degrees C copper column is good for 195 amps. Now we're going to head to our respective tables, and we're going to find the temperature correction factor for 68 degrees C. We're being sure to start on the Celsius side of the table on the left-hand side. And then we have to be very careful here. So we start on the left-hand side because our ambient temperature is in Celsius. But then we have to make sure that we tee off all the way over in the 90 degrees C column. We find that it's a 58% correction factor, or 0.58. So we're going to take our original ampacity, multiply it by 0.58, and that's going to give us a new allowable ampacity of 113.1 amps. And we select A. Great job. What is the allowable ampacity of a 1-aught THHN aluminum conductor that's installed in a pipe with 8 current carrying conductors in an area with an ambient temperature of 42 degrees C? We're going to start in the 90 degrees C column, and we're going to find out that 1-aught aluminum in the 90 degrees C column is good for 135 amps. Now we're going to do our bundling adjustments. We find out that for 8 current carrying conductors, it's 70% or 0.70. Now we're going to do our temperature corrections. We find out that when we're dealing with 42 degrees C, remember we have to make that distinction. When you're dealing with Celsius, you're going to start on the far left-hand side, go down and find your ambient temperature, and then you have to come all the way back across to the 90 degrees C column and make sure that you select the correct factor. And we're going to do 87% or 0.87. And we're going to take the original opacity of 135. We're going to multiply it by 0.70. We're going to multiply that by 0.87. And that's going to give us a new allowable ampacity of 82.215 amps. And we're going to select C. What is the allowable ampacity of a number 6 THHN copper conductor that's installed in a pipe with 4 current carrying conductors? When we're doing temperature corrections and bundling adjustments, we're going to start with our ampacity in the 90 degrees C column. We find number 6 in the 90 degrees C column is good for 75 amps. Now we head to our respective table, and we're going to find our adjustment factor for 4 current carrying conductors is 80%. Now we take our original ampacity, multiply it by 0.80, and that's going to give us a new allowable ampacity of 60 amps, meaning that this wire can now only carry 60 amps safely. And we select C. What size copper THHN service conductors would you select for a dwelling unit with a total calculated load of 49,250 VA on a 120-240 volt single-phase system terminating to 75 degrees C terminals? We're going to divide the total VA by the system voltage. With single phase, we can do straight math. We take our total, divide it by 240. That's going to give us 205.2, and we're going to round down. Now we're going to head to table 240.6a for the next standard size, which is 225 amp. When we're doing service or feeders for the entire dwelling unit, on dwelling units that are in between 1 and 400 amps, we can do the 0.83 reduction and then size the wire based off of that value. 225 multiplied by 0.83, that's going to give us 186.75. Now we're going to head to our primary ampacity table. We're going to head to the 75 degrees C column for copper, and we're going to select B. Great job. What size main overcurrent protection would you select for a total calculated load of 142,250 VA on a 6-unit apartment complex on a 120-208 volt 3-phase system? So we're going to divide the total VA by the system voltage. With three-phase, we're going to do a little pre-work. We're going to do the multiplication of 208 multiplied by 1.732. That's going to give us approximately 360. When we divide our total VAs by that number, that's going to give us 394.85 amps. We're going to round up to 395. Then we're going to head over to table 240.6a. We're going to choose the next standard size, and that is going to be C. Let's get to it. What is the total general lighting demand after demand factors for a dwelling unit that has 3,300 square foot of main living space with a 400 square foot front porch and 1,100 square foot attached garage? We're going to count the 3,300 square foot of main living space. We're going to omit the 400 square foot front porch, and we're going to omit the 1,100 square foot garage. We're going to do 3 VAs per square foot. That is going to give us a total of 9,900 VAs. Now we're going to add our kitchen and laundry circuits with a total of 4,500 VAs. That's going to give us 14,400. Now we're going to head to table 220.42. We're going to subtract our first 3,000 VAs at 100%. So we take our total minus 3,000. That's going to give us 11,400. Then we're going to take that 11,400. We're going to multiply it by 0.35. That is going to give us 3,990. Then we're just going to take that back and add it to the 3,000 that we set aside. That's going to give us 6,990. And we select C. Great job. What size main overcurrent protection would you select for a house with a total calculated load of 189 amps on a 12240 volt single phase system? So all the work in this case has been done for us. They've already given us the amperage. They told us the voltage. Let's get to it. All right, so we have 189 amp load. We're going to need to head to 240.6a. We're just going to choose the next standard size, and we're going to select C. What is the total HVAC demand for a dwelling unit with the following loads on a 12240 volt system? Air conditioning, 25.5 amp compressor with a 3.2 amp blower motor for the system. Heating, 22 kW heat strip. So with the standard method, we're going to use the larger of the two. First, we're going to do the AC. So we just take 25.5 and multiply it by the system voltage, and that's going to give us 6,120 VAs. Then we're going to take that and get in the practice of multiplying it by 1.25, and that's going to give us 7,650. Now we're going to add the blower motor. We take 3.2 multiplied by the system voltage, and that's going to give us 768 watts. Then we take that, we add them together. That's going to give us 8,418 VAs. Now let's add the heat. So we take the 22 kW, and it's a part of the same system, so we're going to add the blower motor. We take and add the blower motor. That gives us 22,768. And we're going to line up our AC and our heat. We find out that our heat is larger, so we're going to omit the smaller, and we're going to select C. Great job. What is the total demand for the following fixed appliances? A 1,500 watt dishwasher, an 1,100 watt garbage disposal, a 3,500 watt water heater, a 1,200 watt central vacuum system using the standard method. All right, first we're going to total all of our fixed appliances. So we just add them all together. That's going to equal 7,300. Then we have to remember the 75% rule for demand factors for 4 or more fixed appliances when we're using the standard method. So we just take our total, we multiply it by 0.75, and that's going to give us 5,475. And we select A. Great job. What is our total general lighting demand after demand factors for a dwelling unit that has 4,300 square foot of living space, a 400 square foot sunroom, and an 1,100 square foot detached garage? First, we're going to count our 4,300 square foot of main living space, and we're going to count our 400 square foot of sunroom. We're going to omit the 1,100 square foot garage. We're going to calculate that at 3 VAs per square foot. That's going to give us a total of 14,100. Now we're going to add our 2 small appliance and 1 laundry circuit totaling 4,500 VAs. And that's going to give us a total of 18,600. Now we're going to head to table 220.42. We're going to take our first 3,000 at 100%. Then we're going to take 3,001 through the next 117,000 at 35. And we're going to take our remainder at 25%. So we take our 18,000 total VAs and we're going to set aside 3,000 at 100%. So we just subtract it from our total. 18,600 minus 3,000, that's going to give us 15,600. Then we're going to take that 15,600, multiply it by 0.35, and that is going to give us a new total of 5,460. Now we must add them back together. We take the 3,000 that we set aside, we're going to add it back to our one that the demand factor has been applied to. Now we are going to total them. That's going to give us 8,460. And we select A. Great job.
This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the pro version with the unlimited testing center and the free version without the unlimited testing center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it.